this video, I'll explain the approaches I took for my project titled Deep Learning Approach for Classification of Skin Lesion and Cancers. My aim was to use different deep learning techniques to classify skin lesions to improve efficiency and potentially reduce workload on healthcare professionals. I started by downloading the dataset from Kaggle, and I copied them to a different folder. I saw that the images in the dataset were split into two different folders, so I copied them into the same folder. This is the total number of images in the dataset. I found that the dataset only had 514 unique images of lesions, and it contained duplicates. So I decided to use only the original to prevent data leakage. This is the metadata. I used the image ID, which is the same as the name of the image file, to create a new column, image path. This is the distribution of images for different classes. Here I've used label encoder to convert the classes into different labels. I then convert the classes into numbered labels. I've split the dataset into training set, testing set, and validation set with a split of 80%, 10%, and 10%. Since the dataset is imbalanced, I've used random oversampling to increase the dataset size by randomly duplicating the images in the minority classes. This is weighted random sampling. This gets the weights for each samples, each images, and the probability of the image getting chosen is based on the sample weights. This is the distribution after using random oversampling. This is the normalization I've used and the image augmentation. I've used this mean and standard deviation because the Pruitt models use the same ones, and if it's not the same, the models may not perform that well. This class is used to get the dataset data frame. It opens the image from the image path, and it applies transformations to it and returns the images and the labels. This is the class distribution after using random oversampling, and this is the class distributions without using any sampling techniques, and this is the distribution after using weighted random sampler. We can see that because the dataset is imbalanced, not all the classes have an image for this batch. and we can see that random oversampling increases the number of increase the samples in a data set. This function is used to initialize the model. It gets the model weights and it initializes the model with these weights. The weights, the model weights are the weights for these models that were trained on the ImageNet dataset. It freezes all the parameters so they can't get updated. It gets the number of input features from the final fully connected layer of the model, and then the new final layer contains the same number of input features, but instead of 1,000 output features, it's changed to a number of classes that I have, which is 7. The final layer of every model is changed in the same way. I initialized 3 sets of the model to test different learning rates. The first set with all the parameters frozen. Second set with all of them as trainable. Third set with only the last few trainable. This is the training step. This gets the image and then the label and moves them to the same device. It makes predictions, calculates loss, and then it updates the model's parameters. And softmax is used to convert the model's output into probabilities, and argmax is used to get the highest class with the highest probability. Validation step does mainly the same thing, but it doesn't update parameters. Training step the training function brings the validation step and training step together. It uses TQDM to show a progress bar, and it prints the different values, and it saves these different values as well. These are the results from the training, from this experiment. This is for the weighted random sampling using learning rate of 0.001. Atom optimizer, cross entropy loss as the loss function, and I've decided to use a learning rate scheduler to automatically decrease the learning rate when model hasn't improved after a few epochs. This is the training time taken for 5 epochs using the weighted random sampler. This is for the random oversampling, and this shows the training time taken for 5 epochs. Um, um, a model trained on oversam using random oversampling did perform better, but using weighted random sampling was significantly faster, so I chose to use weighted random sampling. This is the training for the ResNet model. This is for the VGG19. This for the swing transformer. The best models were ensembled using soft voting, hard voting, and stacking. In soft voting, the probabilities are averaged, and in hard voting, the final prediction is the most common prediction from all the models. For the stacking, the probabilities of the predictions of the base model is used to train the meta model, and these models then make predictions. So the model chosen was the ResNet, Swin, and the Vision Transformer, and the predictions from these models are then used to train the meta model, which is logistic regression model. This code is for the mobile net, and using the mobile unit, which is used for segmentation. Download the dataset, the ISIT 2018 challenge dataset from Kaggle, but this dataset didn't have the validation ground truth and testing ground truth, so I downloaded them from the official website and then moved them into Colab's local storage. To train this model, I've frozen the encoder, which is responsible for getting the features of the images, and then the decoder, which is responsible for segmentation, is unfrozen. This is the dataset class. It does the same thing as the other dataset class, but it gets the image from a folder instead of from the image path from the data frame. These are the augmentation I've used for segmentation. This is the early stopping, which was used to train every model. This stops the model if improvements haven't been made after a certain number of epochs. I trained the segmentation model using BCE with Loss, Adam, and Adam Optimizer. This is the training function for the segmentation. This gets the image, the predictions, calculates the loss, updates the parameters, it uses sigmoid to convert the model's output into probability, and calculates the dice score. The validation does mostly the same thing, but it doesn't update the parameters. This is the main function that is responsible for printing the training accuracy, epochs, dice scores, and storing the different values, which can be used to use for plotting later. The segmentation model achieved accuracy of 91%, dice loss of 0.83, and a Shaked index of 0.72. The segmentation model was then used to segment the images, so only the target region remains. This is done to reduce noise or anything that might make it difficult for the model to predict the images, like hair or any birthmarks or scarring on the skin. So this segmentation model just segments the lesion, the skin lesion, and isolates them. I've used two models to classify the segmented image, which are the ResNet and Swin transformer, because they perform the best when training on the original dataset. These models trained on the segmented dataset didn't perform as well as the other models.